Hello and welcome to the second video for Handout 2 from a Calculus Supplement to Introductory Physics second semester. Here we're going to briefly cover the topic of the Lorentz equation. So let's take a look at what the Lorentz equation is. So the Lorentz equation is one of the basic equations in physics, and what it gives us is an expression of the total force vector acting on a non-relativistic moving charged particle. So the non-relativistic part, just don't worry about that, but it is telling us that's its limit, one of its limits of usefulness. And what it looks like is this, okay? So this is very much a vector equation. It tells us that the force acting on a charged particle is going to be equal to the charge of that particle times the times the electric field. So in other words, if there was no magnetic field, then our expression would simply be this. It would just be F equals Q times E. And that tells us that for positive charges, where Q is positive, the force vector is exactly parallel to the electric field vector. So you take like a proton and you put an electric field, it's going to move in the exact direction of the electric field. And that's actually one of the basic concepts of an electric field. But what about when you combine an electric field with a magnetic field? Well, now you have that force, that is exactly acting on, on the positive charge. But then you also have the effect of velocity. Because if your charge starts accelerating, then once it's moving, then the magnetic field is going to have an effect. Or if a moving charge enters a region that has both a magnetic field and an electric field, like in the example below, then immediately both fields are going to have an effect. But both fields don't point in the same direction. They point in different directions. And in fact, the magnetic field comes out of the cross product. So its effect is very much dependent on where the particle is moving, and it's going to be exerting a force that is perpendicular to the motion, which is not necessarily perpendicular to the electric field. The magnetic field and the electric field can agree with each other, or they can cancel each other out. But overall, we have to go through the steps, do the vector calculus approach, or at least the vector mathematics approach, to find the answer. And so if you look in the example below, this is really what a typical Lorentz force problem would look like. We're going to be given vectors in I hat, j hat, k hat notation, which I covered in the previous semester of this calculus supplement. So here we have a positron, and the positron has a given mass, and that's because and I give you that because I'm going to ask for the acceleration. We are told the charge of the positron, which is the same charge as an electron in magnitude. And notice that the positron, unlike a proton, has the same mass as an electron. We're given its initial velocity, right, quite fast, so it's a very small particle. And it enters a region of space, so this is where the situation starts, where an electric field defined as E, pointing in this direction, and a magnetic field that has this strength, and then I tell you points in the xz plane at a particular angle, so you have to find the components. And then that's the situation, and then it's all about then what is the initial acceleration of the positron, and then what angle does this initial acceleration make with the initial velocity. So I should backtrack slightly before we proceed. I'll go ahead and label some things. So this is the force on the moving charged particle. All right, and then after this, we'll jump into solving the problem. Here we have the electric field vector. Here we have the velocity vector. So this is the charged particle velocity vector. And here we have the magnetic field. And if you draw on a blank, this just means it's the cross product. Okay, and we'll just follow the rules for taking a cross product of vectors in order to find the overall effect. All right, so mostly this is just kind of going through and doing the math. So it's all about the vector math here. So let's just jump into it. Part A. All right. So we need to find the direction that F points. So what does that look like? Well, I'm just going to start like kind of plugging in the numbers here. I'm just going to write the components for now, so I don't have to carry the numbers over so much, but I'll leave off the ones that are 0 to simplify our expression. So here we're going to have Q. And then we have, so if you look at the electric field, it's got an I hat and a j hat component, but no z hat component. So it points in the positive x direction and the positive y direction, but it doesn't point at all in the z direction. So then I would just have E x times I hat plus EY times j hat, okay? And then the cross product, okay? So then I'm going to have V crossed with B, okay? And I'll do that down the next line. So we'll make some a little bit more space. So we have Q, and so EXI plus EYJ. All right, and so what is this going to look like? So the overall cross product is, so let's just make a little note that'll be a helpful reminder for me as well, is that if you think of it, think about how to kind of track the cross product. It's useful to draw what's called a 3x3 determinant, but it's really just a tool for working it out. And so here we have Vx, Vy, Vz, and here we'd have Bx, By, and Bz. And this way you can go through and remember, how to do it. So the first term of the cross product is going to be Vy times Bz minus Vz times By. Okay, so we look at that and we see that the velocity does have a y component. So we'd have Vy, and then we multiply that by Bz. Well, does our magnetic field vector have a z component? Well, we should actually kind of take a step and find the magnetic field. So let's go ahead and do that. Pull us down just a step. So I'll say to find the magnetic field. So I'll say first express B as vector. Okay, and specifically vector in I hat, j hat notation. I'll leave that implied. And so we look at it, we're told its strength, and we're told that it's in the xz plane, and it's and positive x, positive z, and then it's 20 degrees relative to the x-axis. So that means that its x component would be cosine of 20, and its z component is going to be sine of 20. So then we just have b times cosine of 20 degrees, and that would be on the I hat axis, and then plus the magnitude, and that's just the magnitude is given there, times sine of 20 degrees on the k hat, okay? So in other words, B has a x component and a z component, but it doesn't have a y component. Okay, so then going back down, we were left off there, so indeed there is going to be a z component. And then we're going to subtract Vz times By, but Vz is 0, so we're in the clear. This is just going to be 0, okay? And that's all attached to I hat. And then we're going to do the same thing for j hat, except this one we have to subtract. And that's always something you have to remember. And I also need to make this bracket so we're clear. That would only really matter if we had a negative here, but still, good policy. So because whenever we do the I one, that's the one where you have to do the split across, and that's the only one that has a leading negative. And so that would be Vx times Bz, and which would again be positive. So Vx times, or at least non-zero, I mean. And then Vz times Bx, well, that's 0 again. So we're good there. Okay, that's j hat. And then we finally got k hat. I want to put this on one line, so let's pull this over a bit. All right, oh, didn't mean to do that. Okay. All right, so let's bring this over to here. There. All right. And so finally the last term, this one's positive again. This is going to be Vx times By. All right. Well, there's no y component, so that one's is just going to be 0. And then Vy times Bx. Okay. So minus Vy times Bx. And notice that's actually the first time that the magnetic field in the x direction has shown up. Yeah, which makes sense actually, because it wouldn't. Actually, it could have easily showed up in the j hat component, but it didn't because Vz was 0. Okay. All right, there we have it. Close those, and also the final parentheses. Probably bad policy of parentheses outside of a bracket, but hopefully you can forgive me. So now we just have to pull everything together, pull everything that's I, pull everything together that's j, and just kind of go from there. So we're, at this point, it really is just kind of the brute force. So, and I'll probably kind of wrap things up and not show all the numerical solutions, just in the interest of kind of showing you the approach and getting the video done. So we have Q and yeah, I'll kind of put everything together. So at this point, I'm just going to put everything together that is on each direction. So I'm going to find everything that is attached to I hat. So that's going to be Q times EX plus Vy times Bz. So it'll be Q EX plus, well, Q, VZ, or Vy, BZ, okay? And that's it, both positive, and that's all attached to the I hat direction. Okay, so that's what's going, that essentially, that is the sum that is going to be causing a component of force that points in the x direction, right? When you think about it that way. Okay, and then let's do the next thing for the component of force in the y direction. Okay, so we'll start off. We have Q, E, Y. And then what else is going on? Well, in that case, we're actually going to have minus Q, V, X, B, Z. Looks good. All right, so that's everything in the j direction. And then what's going on in the z direction? Well, there's nothing from the electric field side of things because there was no component of electric field in z. But there is one thing going on in the k direction, and that's negative. So I'll just make it negative. V, Y, B, X, K. Okay. All right, so at this point it's just, oh, I left the Q off there. There it is. All right, so at this point it's really just a matter of plugging in all the numbers, and then we've got our force vector. And then once we've got a force vector, then we can just solve for the acceleration vector by dividing by m. Okay? And so, and then we'll point out that the acceleration vector is just going to equal whatever numerically we get divided by m. Okay? And then as far as part B, I do want to mention that briefly. It says, what angle does this initial acceleration make with the initial velocity? Well, to find an angle between two vectors, the way to do that is to use the dot product. So we'd use the dot product to find angle between V naught and A, called A naught, and I'll label it as that as well. All right, because that's really is just the initial, and really it's totally fair, and I probably should also refer to this as the initial force, because a moment later the force is going to be different because the velocity is different, which makes the force different. So this isn't a constant force by any stretch of the imagination, because the magnetic field is dependent on velocity, right? And force changes velocity. So we have an incredible dependence there. So we're certainly not solving for any time-dependent behavior. We absolutely do not have the tools for that. But what we do have the tools is find an angle between two vectors. And what I mean by using the dot product is, no, I wrote not product. So use the dot product. Whoops. Is what that looks like is we would write the acceleration, the initial acceleration, dotted with the initial velocity, by definition, is going to be equal to the magnitude of the initial acceleration times the magnitude of the initial velocity times cosine of the angle between them, cosine of phi. So that's what we're trying to solve for, okay? And then the dot product, one way to express the dot product is just it's the sum of the products of all the equivalent components. And so then what this looks like is the following. We would have AX, or as A naught X, times V naught X plus A naught Y times V naught Y plus A naught Z. Well, that's the thing. V naught Z is actually 0. So it would just be times 0. So that one we know right away, because V naught Z does not exist, that this component is going to 0. All right. And then that would be equal to their magnitudes. Well, what do the magnitudes look like? Well, we just get those from the three-dimensional Pythagorean theorem, the distance formula. So this would just be A naught X squared plus A naught Y squared plus A naught Z squared. And then multiply that by the same thing for velocity. Here with the velocity we can get away with just doing two components because it doesn't have a Z. So it'd be V naught X squared plus V naught Y squared. Okay, so that's what they're equal to. And then times cosine of phi. And so then phi would just be equal to cosine inverse. And here I'm going to use the magic of the tablet to cheat a bit here, because then I can just take this expression, copy it over, because that's going to be my numerator. Put it right there to make space. And then in my denominator, I just divide by the product of the magnitudes, which I've expressed here as the square roots. All right, so there we have it. So that expression right there would be the angle between our two vectors, our initial velocity vector and our initial acceleration vector, due to the combined force of the electric and magnetic field. So kind of neat. All right, and you're going to do one of these for your homework. Basically, the only difference is I've changed some of the numbers, and I asked kind of a mix of a follow-up question. Although I will warn one thing, is that make sure you pay attention, because here I give you a negative charge. And remember, negative charges experience forces that are exactly anti-parallel to the electric field. So don't forget to include those negatives.